Welcome to this week's paper reading. I'm going to share my screen real quick. So we're going to wait for folks to kind of hop in the room for the first few minutes. And so while we're waiting for those people, maybe we can get kicked off with some introductions. So my name is Dat No. You might have seen me in previous paper readings, but really excited to talk about today's kind of paper reading, which will go into depth. But I'm a solutions architect here at Arise. I build pretty heavily with our customers, kind of at the ground level. Get to have my hand in what people are building, why they're building it, maybe the issues that they're coming across. So I definitely really love our paper readings where we can go kind of deep into some technical, what's the edge of knowledge and what are people doing. But I have a special guest here with me today. His name is Vibhu, and I'll let him introduce himself.
Hey, I am Vibhu. I do a lot of LLM stuff, just general AI engineering. That's a homie, so we're talking through video gen stuff. Not the deepest background in video gen, but this is kind of how our conversations go. We find something interesting, we go deep on it. That's how it is. Some of you guys might have seen me around SF, or I help out in the latent space paper club. We run another paper club, so maybe we know each other from there. But yeah, we figured Sora's out. Let's talk about it, see what's going on. Try to go deep. The technical report had quite a bit of info. We'll kind of try to understand what's going on here. And then that with Arise, they're the go-to for evals observability. So we'll start to like talk about that, bounce ideas off each other.
Yep. Yeah, and just to preface, yeah, I don't really know too much about video. I didn't really know much about like video evals or how videos are generated until I started kind of diving into this research. So actually really excited to share with the audience kind of what we figured out and what we know. But maybe to get us started, Vibu is going to walk us through the Sora paper, and then we'll talk about that, and then we'll save the second half for video evals and how people are thinking about that space.
Cool, sounds good. Let me share my screen.
Oh, looks like we have Jason.
Ooh, we got
Hey, Jason,
Jason.
how's it going?
We
How you
just did
doing? Hey,
intros.
Vibu. Hey,
Jason,
Dad.
introduce
How
yourself.
you doing? Awesome.
If you want to do a quick
Awesome, awesome.
introduction, Jason, that'd be great.
Yeah, just founder and founder of Arise here. Great to see everyone.
Awesome. Go for it, Vibu.
Awesome. So we're gonna start going through Sora paper, Sora technical report. We'll kind of just talk through this pretty casually, see where we end up, you know. We're not the deepest on video gen stuff, but Dad and I were kind of talking about it, reading it. I think there's quite a bit of information here. I did some digging. We'll have some fun stuff to share. So most people have probably seen this take over Twitter. Gemini, Google released some interesting stuff within an hour or two. OpenAI's like, actually, hold up, we're gonna take the spotlight. We got Sora, we got crazy video gen, we got like a full minute of really, really solid video gen here. And yeah, we're like, this is going on. Let's try to understand it a bit more. Let's see what's going on. So one thing that I kind of noticed was pretty interesting that people haven't really been going over too like in depth is they came out with a technical report on Sora, and this kind of like tells you a lot about what's actually going on, how they got to it, what the model is like, how people can kind of like reclaim this, what we can expect, how will this break down into open source, and like kind of just think about how video gen will affect the industry. So going through here, I'm just going to kind of note out like some interesting things that I found while reading through it. We'll get opinions from Dat and Jason, see what we're thinking about. So first thing I thought was like pretty interesting was right here. They say this line that like people aren't tweeting enough. Our largest model, Sora, is capable of generating a minute of high fidelity video. Largest model. So are they like talking about, you know, compared to Dolly, compared to GPT 3.5, compared to GPT 4? The technical aspect of how like text to video works means that like this is a pretty heavy model. We'll try to like break down some rough numbers of like how they're doing this, but yeah, it's pretty big. So if this is like their largest model, you know, is this like GPT-5 equivalent? Is this the future of where they're taking things? I thought that was kind of interesting. Overview though, there's a transformer architecture. They're doing space-time patches of video and latent image codes. It's a very large model. They're able to scale video generation models. They talk about simulations, physical worlds. I know there's like interesting takes on that. Jan LeCun from Meta is kind of against it's not really a great simulator, but then we have others like Jim Fan from NVIDIA is like, wow, this is great simulation. But yeah,
That was a
Jason,
heated
that
argument. I don't know if you
yeah.
saw the Twitter thread on that. And um I think, I mean, people have really strong stances in this where it feels like the jury's still pretty out. I'm surprised people, Jan versus Jim. There's kind of like there's definitely a world model and not a world model view of how these things work. And I tend to be a little more balanced and say like either side could be right. Let me get more information, but very, very interesting, heated, physics simulator debates.
Yeah, it's so interesting because like for people that are still watching and haven't really gone too deep, Sora is not out yet. Not many people can play around with it. It's still being red
Yeah.
teamed. They made claims and they show demos, and I don't know, there's a lot to go off of with just that, you know? So
Yep.
it's interesting how strong the stances have been. I'm pretty neutral on this as well. One, because I also don't have as much of a background as these two to make these claims,
Yep.
but also, yeah,
Yep.
we haven't seen the evidence. There's some interesting like takes that have come out too, where they're claiming that they can generate a minute of like temporally consistent video. But then people have pointed out that like every sample on Twitter, every sample on the website here, I think the longest clips are like 17 to 20 seconds or something.
Mm.
So people are like, this is transformer based generation. Does it hallucinate after a certain amount of time? Are they doing these intervals for a specific reason? Why can't we see a minute video? So there's still a lot of gaps that really need to be filled before you make these assumptions. But either way, for the casual people, you know, it's fun to read these very smart people take these takes. But following, I thought that this technical report was actually really interesting because they have a whole bunch of resources. I feel like they really gave a good like overview of how they came to the approach that they came to. So when going through this, they kind of link like for everything they talk about, I think a total of like 30 citations. And if someone's really interested in text to video and how they like get this architecture, there's a lot of great resources here. So they kind of stay how like previous work used RNNs, then we used GANs, autoregressive transformers, diffusion models, all this stuff kind of built into Sora, how it comes to be. And then if you click any of these links, you have like a great reference of papers to go through and like better understand the scene. So for someone that, you know, wants to shed more light in this, there's a lot of reading to do here. And a second follow-up as well to like understand the complexities of this. If you look at the general Sora release, not just the technical paper, I did some digging. I looked into who's the research lead, who's the systems lead, who are the contributors. If you kind of look into these people, you get some of their background. What have they focused on? Where does their research excel? And something interesting was like, there's a lot of the Dolly team that's working on this. That's a key component of Sora. They kind of go into this in the technical research paper. But then there's also a lot of like inference optimization. So it kind of gives you an idea of, okay, this is our largest model. How do we run this? How are they going to scale it? Why haven't they deployed it? You can get a rough idea of how this generation is going. And then something that I was surprised by looking at these people is like how much work they've done on like effectively deploying inference of transformers. And it seems to me like that's a really big thing. That's why they haven't released it. How long will this take? People are saying it could take like an hour for a minute of video. How do you do that right? How do you get it to stick to the prompt? This kind of goes into evals as well with like there's a truthfulness score of how well the video actually sticks to the prompt since
Mm.
this is kind of different than text gen, right? So we
Yep.
have to make sure that there's quality. It takes time. Inference is really heavy. What's the cost of all this? But
Yeah.
yeah, it's only been a few days. I think go
I
through people, go through papers.
Yeah, I think one of the things that surprised me in this was that, and I hadn't seen this before, maybe I missed it, but this there's a paper of scalable diffusion models with transformers. So this is a transformer based. So if you look at the paper there, it's like Peoples, Williams, Sanding at the end. And it's basically a transformer based diffusion model, which I didn't even myself know existed. There was a paper out this last year on it, and there's like a unit backbone of typical diffusion models that they replace with a transformer. And I think the goal here is just to be able to use the same scaling, training architectures that they've perfected for other things for diffusion models. But I thought that was one interesting take that I hadn't seen here. or had it
Yeah,
knows?
they go pretty deep into this actually about how it is transformer based, how they actually break this
Yeah.
down. Like, so they have visual patches of video where basically video is just images stitched together. So basically you take video, you break it down into image patches. They have like a 3-step process. There's a visual encoder. You get this to a lower dimension latent space. That's where generation kind of occurs. And a lot of this kind of also goes into bitter lesson of just, hey, what worked was we scaled all this up. They kind of have an example here as well of like early in the steps, it's not so great. Train more, 4x compute, it gets better. 32x, the more compute you throw, the better it gets. They're kind of really using that, like they talk about emergence, the scaling of transformers and how this works. But yeah, they have a lot of that in this technical report here. And once again, great papers that like they reference. Essentially, what's going on here is similar to stable diffusion, where you generate images from noise. What they're doing is they're generating videos from like padded noise and they're filling in the gaps. And the way that they learn some of this like physics-based simulation is as you're generating and filling in like time sequences of noise, you're kind of looking ahead, right? So we're filling in how would this video be created based on like the future goes here, this is the current, and it's kind of learning all the simulation in and of itself. And they go deeper into how all this works depending on how technical we want to get. We're probably just going to go roughly skip it over just for the sake of time, but it's all stuff that I found interesting that people would want to dive down. I think that here they gave some like interesting insights into how big this is, how it runs, what's actually going on. So when you're doing stable diffusion over time for videos, it's no longer auto regressively generating. So basically you like subsample down into a latent space, you generate a bunch of sample images with temporal consistency, and each of these frames has to be generated like not sequentially in the sense of it's not sequentially. It's all happening at once. So you no longer have benefits of like KV caching where you can look at previous frames. So the inference for this is like significantly more expensive to do this as it gets longer. There's more research that really has to go into that, which is why when you look at the authors, they're very like focused on infra deploying this. I thought that was kind of interesting. You can do rough calculations of like, let's say the latent space that video is generated in is like 16 by 16 times 30 FPS times 60 seconds. That's about roughly half a mil tokens that have to be generated, similar to GPT-4, but now it's not autoregressive with KV caching. So it's just compute heavy, and we don't know the exact number. So it could be higher, it could be smaller. There's infra tricks that they're doing here. But I thought that's just like, a deeper overview of what's actually going on inside Sora before we talk about the fun stuff of how all this works. Do you guys have any thoughts? That was like my deeper take of how this actually works. And then they have like little parts anywhere in the paper we should scroll through. Let's go deeper on those sections.
Yeah, I think it was a good take. I mean, I probably don't like. I feel like I need a deeper it's a little surface level, and then I think there's a fair amount of references that I still feel like I haven't gone through. So I still feel like this is kind of a lot of this is decently new to me as I'm kind of taking it in myself. But
Yeah, I thought that was a good take, and I like the napkin math, Vibhu. Would you, in terms of like when you think about the inputs for compute, so it sounds like pixel resolution obviously is a component. The number of frames you're generating, right, which maybe is a function of, it's probably total frames, not like the length of time, because you could have like 60 FPS, but then generate for 2 minutes is the same as like 4 minutes at 30 FPS. So do you think it's not only the resolution, the number of frames? Do you think there are any other inputs to compute here that people should be thinking about?
Yeah, so a lot of this is pretty abstracted away because it's not an open source model. They don't share the architecture, but what they do share is that like they have a desampling step where they come down to a lower dimension. So they have like an encoder that takes it to a lower dimension, like latent space. They do generation at this dimensionality, then they upscale it back up. So these are really rough numbers. with a pretty like low estimate, or I could just be all off here. I also don't have a great video gen background, but it's just an understanding of what's going on here. And then if you understand it at that level, if you're actually building with it, you can better understand like what are the limitations. This is like why there's still benefit to understand what attention is, how LLMs work, because you kind of understand their inherent like the issues that you might run into there, you know? But napkin math is napkin math. A lot of this is just kind of abstracted away as it is.
Totally.
I think some other interesting stuff that's like a little higher level and not as low level is how they got their training data. So there's some interesting stuff about like Unreal Engine and like labeling their clips. One thing a lot of people didn't realize last year, like OpenAI put out an actual research paper. So DALL-E 3 has like an actual research paper. They don't share architecture, but they do share like how they got from DALL-E 2 to DALL-E 3. What were the advancements? And a lot of it is just synthetic data captioning. So they have a really good captioning model that they use to train data. A lot of Sora, it seems, is based on that. And you can see the DALL-E people worked on it. So a lot of the like text video clips are captioned similar to DALL-E with a GPT style synthetic data captioner. They're able to like really leverage that to have good video generation. So higher level, that's kind of also what made this possible. Another aspect is, as they say with their scaling laws and everything, just throw more compute and it gets better. It is a transformer based. They
Yeah.
talk about previous approaches. They build on stable diffusion work and everything. So that's kind of where they went from there. There's other like capabilities for people that haven't followed what Sora is. So there's some cool stuff here like animating DALL-E images. So taking image to video, extending generated videos. So kind of like going forward in time, going back in time, looping video generation. Some of this stuff gets pretty trippy. Some people have noticed that like as you scroll down, the examples aren't as good. Was this just to kind of steal the hype of like Google released a big model? Here's kind of what we have ready. It's not super ready. This is also like pretty common in stable diffusion, stable video, video to video generation, but a lot of it is just pretty interesting that like they have all this in one model, you know, like it seems like it's a pretty foundation like big move for them and they've announced it. Some of it is like blending in two videos. So going from like one video to another, blending them in properly. So like we have this and this, and then we combine them. It works pretty well. There's a lot of talk on like how this affects the industry. We've kind of gone 0 to 100 of like what wasn't possible to what is possible. How much does stock footage still matter? It has the ability to also just straight generate high res images. You don't have to do video. So there's a lot to Sora, you know? I'm curious, outside of like the paper, you know, what did you guys find most interesting without going
Yeah.
too technical? Just, yeah.
Yeah, I was gonna, I'll kind of share two things, share a couple um things that I kind of ran through and kind of like look like going through the previous research. So the first one, yeah, maybe everyone knows it. I don't think I did, which was diffusion models with transformers. This is kind of one of the backup papers I was just mentioning. Again, replacing the base of it with that, and then I thought this one was kind of a useful one, which was the patch impact. So again, these are from the references, but it gave an idea. And by the way, from you know deep mind folks, um, the idea of like the patches and understanding, turning a patch into an image here into a set of patches, and those patches become latent space embedding, latent space embeddings. And so like you're mentioning, if you think about like each one of these little squares is a token, or and so your basically scale is going to be how many patches do you have in an image, how many images do you have in a sequence. That determines how many tokens or inferences you're going to do. So that's kind of comes back to what you were talking about previously in terms of scale. um I thought this was, a good visual, a good interesting view of it. And then I thought that was pretty funny too. I saw some of the comments on Twitter where, this was, I think, from Dilip, that basically I didn't realize that this is one of the original authors the original paper authors of, I guess, the VIT transformer, someone who works on the VIT transformer, and the VIT transformers, one of the running up names was, TOP, which is transformer on patches. So so the idea of patches and the idea, I think Dilip was kind of hinting that Google had driven some of this, or kind of some of these ideas, and so some of the concept of patches is not new, and is part of kind of the VIT transformer work being done. But I thought these were kind of useful backgrounds to understanding how the patches map the latent space, and understanding that. The other one I thought was pretty good, which is this thread, if you haven't seen it, which is what I think Vibhu was referencing, which was like the hot topic, which was like, I think, again, this gets into the theoretical, like hypothetical debate space, which none of us really, a lot of you can tell, like, people who really know this stuff still have very differing views. And the question's like, looking at this video here, water looks pretty good in its motion. Like has it learned the physics of is it modeling any of the physics behind what's there? And that's kind of the debate. And Jim Pham's taking one side of this, which is kind of that it's learning some physics. I don't think he thinks it's got the physics perfect, but his stance is there, there's physics being learned, and there's a hot debate of people saying no, it's not. And there's some examples here where clearly the physics is a little unique. But
I think the hot take there too, Jason, is like, so for people on the podcast who can't see this, it's a picture of like a glass kind of falling, and it doesn't shatter. And it's actually in like the research paper too, where like Sora does have limitations, right, as a simulator. So like, do I think this is just like prompting Unreal Engine 5? I don't think it is. I think it's like it's approximating motion from all the videos that's been trained, but it's actually, I don't think is a physics. Like I think it kind of understands video, but I don't think it understands physics. So anyway, that's my hot take. Vibhu, I don't know if you would agree, or Jason, what are your thoughts if you want to share your hot takes?
I think it learns the model. I think it learns the model, the data it has. And as much as some physics exists in that, it might learn some of that. And I think that's where some of the Jim Pham hot takes are. I think the Jan LeCun hot takes are there's no truth. Like I think Jan LeCun's got a couple really big digs on these generative models where because there's no true ground truth, it's not learning physics in the real world, that what it's learning just doesn't match necessarily the real world. It's not learning the true world model. And then I think there's other hot takes on just generative models and how they work in general. In terms of the accuracy of the outputs. So I think there's kind of a couple sides. Both have some grounding in truth and reality. I mean, they're both kind of amazing in the space, but I think there's some truth to both. I think it's learning. I mean, it definitely learns. I think we've felt it with even GPT-4, which in Gemini and all these other models, that they learn some model of the data. They learn some representation and modeling of the data. It's not just next word. There's something more structural they're learning. And the question is, are those structural things? Sorry. Okay, go ahead.
Yeah, I'm sharing, Jason. Okay, that's a good segue. I know I want to save the last maybe 15 minutes for. So we did talk about like this brand new model, Sora.
Can I throw in a take or two, by the way? Just on those. Yeah.
Sure.
I think that, well, I don't have like the biggest, it's simulation, not simulation, but there is other stuff that people have brought up that's valid. Like, it doesn't process audio. There's a lot of studies that show like in simulation, to have real world understanding, audio is pretty key, right? I think TikTok has like a thing that 88% of like users would not see it the same without audio. So like there's a lot of that as well. But on the vision transformer stuff, actually, it's interesting. So one, there's a tweet out from someone at Google that's like, Sora announced, rebranded a bunch of Google research because everything is all Google stuff. But then this also goes both ways. So the kind of history of multimodal models. So like Google put out Vision Transformer, right? And then you have like Clip, which was using CNNs from OpenAI. Eventually, as we got to the latest versions of Clips, they started using a vision transformer for the encoder. But if you look at Google research in 2022, I believe they have Flamingo, which is like a vision language model. And they actually switched back out from using vision transformer back to a CNN. So Google kind of went the other way where they made vision transformer, they like use it a few times, then their latest research with Flamingo, they go back to a CNN and it's no longer, or a resonant, and it's like no longer a vision transformer. But OpenAI is like now using vision transformer. So interesting little tea to dig into. So, they're saying one thing, they're doing another. Anyway, okay, back to Eval.
Okay, no, I like that. That's a good hot take. Feel like they're always building off of each other, as they
They
should.
really are.
Um,
And
okay,
other takes as well. I've like talked to people at OpenAI that like kind of explain how these labs work and stuff. And there's little stuff where like you're not allowed to see what other teams are working on. So like people not working on Sora don't know what Sora team is doing, how it's going and stuff. So, there's probably reasons we can infer for why that is, but
awesome.
food
We
for
have a
thought.
Q&A question from Eric Ringer. Are you seeing examples of geometric slash physical implausibility, like the malformed hands in SD images? If not, what are they doing to prevent this in the Q&A?
Yeah, I mean, it's pretty clear with this picture where you get some of that physical implausibility, and which is, I think, what they were highlighting. It's like, obviously, the glass can't melt into the table. I don't know. I don't know. Hard to say because again, we haven't had to got to play with it much, but I think there's inklings of physics, like Jim Fan saying, and there's a bunch of examples where things just look impossible too.
Yeah, I feel like there's also a fine tuning. Like obviously there's the data that they trained on too. But I feel like there's also some fine tuning steps. And maybe when we go through the evals, we can get a hint of maybe what those
Yeah.
quote
I mean,
unquote.
what's interesting
Yeah.
in this video too, like the glass melts on the table, but the ice kind of bounces off the table. I don't know if you kind of see it as it hits. Like it's learning some model of things. Just I don't know how much it truly represents you know, the true physics. We'll be studying it for a while, I'm sure.
Yeah. I
Some
also think
people
with
have kind
enough.
of
Oh, go ahead, Vivu.
Some people have brought up like edge cases like in self-driving cars where like you get a lot of it now, but then is there a 10-year like it's got ray tracing down pretty well, which is like really new and really hard to do. It gets lighting pretty well, but then some basic stuff like this, is there just a tail ending like, bunch of stuff that it has to keep figuring out? In direct answering the question a bit, they
Yeah.
did say that like they have a detection classifier. So a lot of this pipeline will probably be abstracted away. It's on their end of how they serve this. So like if a generation is like, probably like doesn't match the prompt well, they probably have their own check that we can't do. Shipping this to production is pretty different than stable diffusion images. Right now we have like the LCA models like latent consistency where you can live time redo like image gen, but this will take time. Like I think they've said it could take like, 20, 30 minutes to generate a video. So it's not like
Mhm.
the same UX
Wow.
as image gen. Yeah, these are heavy models. And then
Wow.
as well as that, there's also they have metadata to like show what is Sora generated. They have classifiers for toxicity. So I think that like the direct answer is that they'll deal with some of this. But we do also just see like, yeah, sometimes fingers are off. Sometimes people phase through things. But once again, it's not out. I still have the take of, they were taking some of Gemini's thunder and put out some cooldown. There's no minute long videos, but it's impressive.
Okay, I know we're gonna run out of time. I definitely want to make it
Yeah,
through
go ahead.
eval. So the first section we talked about maybe a big like step function change into generating evals. I think we were all impressed with the physics and just how the videos looked. Maybe we talk about how do people think about maybe evaluating? Because like as a human, you think it looks good, but are there quantitative measures to do this? So I did pull this paper, EvalCrafter by some researchers in HK and University of Macau. But I really like this paper because if I had to break it down, the way they thought about their benchmark, so they set up essentially kind of a bunch of tests. So they kind of walk through um, really how you set up their tests, right? So what kind of prompts to generate whatever videos. And then they have essentially a framework, and this is a really good way to describe the framework down here. They broke down the evals into 4 categories, right? And so there's video quality, text video alignment, motion quality, temporal consistency. So we'll walk through all 4, and I'm just going to do the TLDR based off of time and what they mean and what's the math kind of behind each one. But I really learned that to evaluate video, there's actually a lot of criteria. If you think about the medium of time, it's super important. It's maybe different than maybe text to text or text to image. And so let's maybe walk through the first set of evals. And so some of the eval metrics. So the first one is video quality. And really, there's a few ways that these researchers kind of looked at it. So video quality assessment. This is based off of another paper based off of Dover. And so Dover just stands for Disentangled Objective Video Quality Evaluator. It's essentially a way to measure the quality of that specific eval. And the way they broke it down specifically was in 2 parts. There's VQA sub A and VQA sub T. Basically, I want to measure the aesthetic score, which is the sub A, or the technical score. And so the aesthetic score is essentially, hey, like aesthetically, do I have what I essentially wrote out? So if I have a prompt to generate a video, do I have those kind of overall qualities in that video quality? And the technical score is really technical distortions. So it goes super into depth what VQA and V sub A and VQA sub T actually mean. But the TLDR of it is like, do I have distortions in certain artifacts, etc. So it's actually using another model to assess essentially the generated video. The next, kind of category inside of here is inside of video quality is inception score. And so this is also the inception score is essentially it evaluates again, it's another model and it reflects the diversity of the generated video, right? And so there's a whole paper on inception score and what it means. But it really is trying to like evaluate kind of, it uses what's called like a CAT-GAN to assess like how diverse is, what am I generating? So just TLDR, that's something you can measure. Is like, hey, how generative is this particular kind of video that I'm generating? So that's the first category that we kind of walk through. So they used VQA sub A, VQA sub T, and then the inception score. The next category is text video alignment. So text as in, hey, here's the prompt, and video as in, here's what I generated. And there's quite a few scores in here as well. And so we'll just kind of hop through that. And so when we look at the text to video kind of alignment, there's this first category called text to video consistency. The way you can think about text to video consistency, some people call it like a clip score. You essentially obtain like a frame-wise image embedding and then a text embedding, and then you compute their cosine similarity. And so the idea here is how closely does the text that I have align with this particular image embedding. So it's almost like comparing an image embedding to a text embedding and then seeing, are they similar? You'll start to notice a lot of similarities for quantifying this. A lot of it is comparing embeddings for certain aspects of the video. Maybe the next one to talk about is image video consistency, or some people call it SD score. This one is really calculating the embedding similarity between the generated video and this thing called the SDXL image. The SDXL is go figure a latent diffusion model for text to image synthesis. Anyways, there's a whole other paper about this, but essentially using another model. Oops. So SDXL is a latent diffusion model for synthesis. Essentially, you can do a few things for evaluation. It's like use another model to see if it's consistent or compare sets of embeddings. That's kind of the theme I'm getting from this paper. And so when we think about this score, essentially what this one's trying to measure is the video to an image, whereas the text to video above here is a text to the particular generated. This one was an image. Frame-wise image, yeah, embeddings to text. So a little different, text to image and then image to video. Okay, object and attributes consistency. This is also part of text video alignment. This one's made up of actually 3 scores, and I'm not going to go into so much depth. but there's essentially image segmentation and object detection tracking. So, hey, is this thing that I'm locating throughout temporally in the right place? You can think if things hop around in a video, it kind of makes for an inconsistent video. So actually tracking where things are in a particular frame. Turns out there's models for that, Samtrack. You can use object detection, Coco, etc. But there's ways to quantitatively measure, hey, is the object of interest in my frames moving around? Or is it like kind of consistent in terms of the number that exists? So the number of counts. So if I have 3 objects in a frame, in the next frame, do I also have 3 objects? Color scores, things like that. So hopefully that one makes sense. So that was text to video alignment. So just to cover that, the next section is motion quality. So how are
Also,
things?
if I could pop in for a second, for that
Yeah,
text to video alignment section, it's actually probably it's a pretty interesting one that I would recommend people go down if they're like looking into any of these. A lot of this I would say is pretty abstracted away in the sense of we're not doing foundation models. There's only so many models that we can use that have such generation. So a lot of this we can't do, but going into text to video alignment, like the stuff of comparing image to text embeddings, this is kind of how multimodal models work. So you kind of add another modality to like a language model, and you do contrastive learning by comparing what's the embedding space of this image with this text pair. So this kind of like eval has broader implications to a lot of this. A lot of the other stuff here is like frame by frame, is there consistency? Does motion seem right? The overall quality. Other papers like Emu video from Meta that also like has benchmarks around of this. There's also just like the vibe check of like we have human annotators. We measure these things without with a qualitative eval and
yeah.
like do that. But then this is a good one to go into if anyone's into it, but I'll let you continue.
Yeah, no, that's a good point, Vivu. We will talk about, so the researchers also do a qualitative eval. So this is like the same like thumbs up, thumbs down, but except it's like a set of categories, and that's at the end of this paper. I think the next thing is motion quality. So the really cool thing is for maybe you can have specific scores for specific types of videos. For instance, if you have humans in your video, there's this action score. Essentially, it says MMA action 2. Essentially there's another model that understands like the kinetics and motions of humans, right? So it's like, hey, is this human moving in a way that a normal human would move? You can actually score and measure these things. So you'll start to notice some of these more specialized. So this is like motion quality. Is the human actually walking like a human, moving like a human? Um, we have things like average flow score. And this is just maybe instead of being human oriented, like action score, this is just like, hey, do objects behave like they should? So this is maybe non-human versions of that. So does the flow from this frame to this frame, does this specific generic object work? Then there's this AC score too. And then the way you can think about this is, I really didn't understand this one to be very honest. So I didn't really understand this one, but we can move on to maybe temporal consistency, which is the last one.
If you want, I can explain it for a second. So some
Yeah,
stuff that people find very interesting in Sora is like when you come to animation, there's like 12 key things or something that animated videos do really well. And a lot of that is like what's the velocity of like eye movement and like moving and like animating characters and stuff. And a lot of the other video models have not done this well. It's like they get like a 0 on this score. So this is kind of measuring that, and people have noticed that like inherently Sora has done this very well, even though we don't have benchmarks for any of this. This is kind of talking about like what's fluidity of the motion in images. This goes into animation. If you're like an animation studio doing like a rough draft, how well does your like video generation model actual like motion? That's kind of what this measures. I've never done this eval, but
yeah,
that's kind of the space. And it is very like it's actually a key thing that's like been talked about with other video gen models. It's just not my space. But
yeah. Actually, I,
I'll
I
let you
think I
know.
remember this one. This one's like if you said, hey, human
Yeah.
walking quickly in the frame, and if they end up walking super slowly, it's like, hey, and I know I've never run this eval before, but the way it's kind of described, it's like whether the motion amplitude is consistent with the amplitude specified in the text prompt. My thought is like, hey, if you say a human's walking quickly and they end up walking really slow, I'm assuming there's a way to measure it. Again, this
Yeah.
paper also is the rabbit hole into probably 50 other papers.
This goes deep. There's a lot of overlap in these evals too. Like text to prompt alignment would also fit that, right? Human goes slow, human
Yeah.
doesn't go slow. So I don't know. That's the big one that I go for, just text to video alignment, because the real thing in video gen is like this stuff takes time. It's very compute intensive. That's why they have a lot of people optimizing how to ship this, how to deploy this. And like emo video, I remember seeing that a year ago. What they show is like there's some benchmarks where they can get great video. It just doesn't align to the prompt. So that doesn't necessarily match what we're expecting, right? If you have a great video but it doesn't meet your prompt, there's not much value in that. But yeah, just
Yeah.
other stuff about it.
And I'm gonna go through the last category, and then I have a hot take. But temporal consistency, time, super important in videos. Obviously, we'll cover really quickly what that means. But there's warping error. Never heard of that, but I think it's like understanding. Um, this one I didn't really know super well, but it says we calculate pixel-wise differences between a warped image and a predicted image. I think it's maybe, I don't know, a future prediction versus, I don't know what a warped image means. And then you look at the difference, and it somehow gives you, maybe Vibhu, you have maybe deeper
This
knowledge.
is just like general with temporal consistency, since you're doing stable diffusion. So you're generating base images from noise, stitching them together. Like previous work on video gen, there would be very like deep inconsistency between frame to frame where like backgrounds would change. So warping is where like if there's motion, like let's say I'm moving my hand, in like one frame, I might have 5 fingers, the next I might have none, the next my like face might warp somewhere. So this is like a measure of
Okay.
how do you actually measure temporal consistency. A lot of this is also just vibe check, or there's
Yeah.
like hacky routes to do this very efficiently that we can tangent into another area of research. But actually a lot of like Alibaba, Tencent models, if you think of like the dancing videos and like AI influencer videos, they're very efficient in the sense of like you generate one image, you train a model that like maps dancing motion, for example, and apply that to your image and move it. Takes a lot less compute and it solves this warping. So another rabbit hole to go down, but it's just a
Yeah.
part of temporal consistency.
Yeah. It's like time consistency. This is pixel to pixel. And I think the next one is, turns out you can actually you can look at semantic consistency. So turn a pixel into some text and see if the text is consistent throughout time. Um, There's also face consistency. Like I said, there's very specific things to humans, for example. So I think this one might be like pixel to pixel consistency over time, but maybe more specific to a human's face. And so, anyways, I just want to give people an idea of like maybe the categories that people are thinking about. And for the first time, I think the quantitative measures are just, I think they're harder to do. Maybe I'm wrong. Then they also did a user opinion alignment, which is that feedback. So to give qualitative scores from humans, and so things like video quality, uh, things like that, things when you as a human look at a video, you kind of know something is off, and maybe they have a more qualitative, maybe feedback for that. But for the first time, I think it's like it's interesting to understand how we humans think a video is good, and then how do you get that into math form was really what I wanted to cover in this paper. But any other closing thoughts, Jason, Vibhu?
I want to hear the hot takes.
The only other thought I have is like yeah, these are, I mean, I guess for the creative generative models, you tend to care more about your model evals versus like what we have this concept of task evals where you're trying to like as it's as people are using this in production, getting proxy metrics for if it's working correctly, and they're normally like simplified versions of something, but most of this fit into the model eval category of trying to understand the quality of the model you built in the first place and compare models. Um, when a business goes to use this or a customer goes to use this, and you're looking at like use by use by use, did it do what the person wanted to? There's probably a simple version or some version of this. I mean, for creative stuff, it tends to matter less. You create a bunch of things and you just throw it, like that, the output. Um, if you're integrating GPT-4 into your business system, you care a lot about like not breaking things. For creative image generation, you can just do another one. So maybe those task evals matter less. It's just around getting the model right or good enough.
Yeah. I guess my other thing, that I'm pretty excited about, even with that space, is like
Yeah.
they're doing pretty good like video latent space work, and that leads to embeddings. And I don't know, I like how like Phoenix has the whole like embedding visualization. I want to see more of that for video. If you're taking this to prod, I would love to see a version of like video embeddings plotted in Phoenix, like actually going through that, seeing what fits, how we build pipelines around this. How do you like do this actual like, pipeline work?
Cool. Awesome.
Awesome.
Well, thanks
Well,
everyone for joining, and great conversation.
yeah, big shout
Excited to
out to
get
our
our hands
special
on
guest.
Sora.
Yeah, big shout out to our special guest, Vibhu. If you can't tell,
Thank you.
he's a wealth of information. His contact will be kind of in the paper reading as well if you ever want to reach out to him for anything. But thank you so much for joining.
Yeah,
Thanks, guys.
thanks, Vivu.
Take care.
Cheers.